Hello, everyone. So welcome to the 8th Copernicus MOOC webinar. So we will now start the event. So welcome to all of you. Today we will welcome two speakers. So Dr. Jamila Mifdal, postdoctoral researcher at SAR Team, who will do a presentation about application of optimal transport for hyperspectral and multispectral image fusion. And then we will welcome Oisin Magras, CEO and founder of DroneSAR, who you already met during the module. We will do a presentation about drones and Copernicus data use in search and rescue missions. Both of these presentations will be followed by Q&A session. So feel free to ask anything you may miss during the presentation. And I will now give the floor to Jamila Mifdal, who will start her presentation.
Hello, everyone. Thank you, Benjamin, and the team of University of Luxembourg for organizing this webinar and for doing the test before my presentation. Thank you very much. Welcome, everyone, from wherever you are in the globe. So, my name is Jamila Mifdal. I'm a postdoctoral researcher at the European Space Agency at PhilLab in Italy. And today I'm going to talk about the application of the theory of optimal transport for hyperspectral and multispectral image fusion. So even though there is no deep learning or machine learning implicated in what I'm going to present today, the application of optimal transport for image fusion is a part of artificial intelligence family, and I'm going to explain this in the coming slides. So there's a huge amount of data that arrive on a daily basis from the satellites that revolve around the Earth, and this data needs to be analyzed in order to recover the accurate and useful information. And for this, we use data analysis techniques, which I'm going to talk about in the next slides. And once the accurate information is drawn from the observed, from the recovered data set, it can be communicated to the users. So there are two families of data analysis techniques. So there are model-driven methods, which are based on the physics of the image, and which I'm going to present today. And there are data-driven methods, which are machine learning and deep learning based models. So the advantage of artificial intelligence algorithms are automating tasks and processing them faster than the human intelligence, dealing with a huge number of data and higher dimensional data. For example, as human beings, we can see only 3 bands: red, blue, and green. Red, green, and blue. And with artificial intelligence techniques and algorithms, we can process data with higher number of spectral bands with a high speed, of course, which gives the advantage of extracting much useful information than by a human being. So the application of artificial intelligence in Earth observation are, for example, forest and urban areas mapping, evaluating the damage after a natural catastrophe, or also monitoring the climate change. The problem that can happen with some of the methods, for example, all the methods that are based on machine learning techniques, is the lack of labeled data, because we know that, or as some of you might know, machine learning or deep learning based technique works better when we have big amounts of data. Okay, so as I said before, so there are many satellites that communicate a big amount of data on a daily basis, except that most of the time, these satellites or the imaging sensors on board of these satellites are subject to constraints, financial, of course, but also technical constraints, such as the onboard storage capacity, the acceptable signal to noise ratio, the power of the incident light, etc. And these constraints lead to acquiring a limited resolution. Leads to a limited resolution in imaging sensors, which leads to acquiring images with low resolutions, either in the spectral domain or in the spatial domain. So most of the time we can have either images with a high spatial resolution and a low spectral one, or vice versa. We can have an image with a high spectral resolution and a low spatial one. So what I'm going to present today is how to take advantage of the information contained in data with low resolution in the spatial domain and high resolution in the spectral domain, or vice versa, in order to produce a high resolution image. So here we have two examples. So we have hyperspectral data on my left, which has a GSD of 30 meters. I don't know if you're familiar with the GSD, which is the ground sampling distance, but I'm gonna explain it briefly. So a GSD of 30 meters means that each pixel on the image represents an area of 30 by 30 meters squared on the Earth. So there's a lot of information that is squeezed in one pixel, which leads to a degraded spatial resolution. But on the other hand, these kind of data has many spectral bands, so it can be useful for example, studying the concentration of a gas in the air, identifying plant species, mineral mapping, etc. On my right, we have a multispectral image which has a GSD of 5 meters, which means that each pixel represents an area of 5 by 5 meters squared, which means that we don't have a lot of data squeezed in one pixel, which means that the spatial resolution of the image is better or good than the one of the hyperspectral image. But a hyperspectral image doesn't have many spectral bands, so it has a very limited amount of bands. And these kinds of images, which are good spatially, they can be used for object detection, object target detection, land cover mapping, etc. So the goal is to fuse the number of bands in the hyperspectral data and the spatial resolution of the multispectral data in one fused image, so that this image is good spatially and spectrally. Okay, so here I have a small scheme of two images. So I have the multispectral one, which has 4 bands and a good spatial resolution. So this image is named F. So big M is the number of bands and big N is the number of pixels. And we have a hyperspectral image named G, which has big H number of bands and NL number of pixels. And the goal is to fuse these two images in order to have an image U that has big H number of bands and big N number of pixels. Okay, so now I'm going to speak about the theory of optimal transport by introducing a few examples. I don't know if some of you are familiar with this optimal transport, with these theories, but maybe if I tell you Wasserstein guns, it's going to ring a bell. So Wasserstein distance is a crucial tool and distance in the optimal transport theory, and we're going to see it later in the slides. So the first image on my left represents a 3D interpolation with Wasserstein barysensor. So we have 3 objects, a torus, a duck, and a hippopotamus. And with multiple interpolation coefficients, we generated many interpolated objects. And we can see that each time for each set of interpolation coefficients, we have a new object with a clean shape and the geometrical properties, and it's pleasant visually speaking. On the right, we have the comparison between the Wasserstein barycenter and the Euclidean barycenter. So the Euclidean barycenter, we can see that it's messy. I mean, whenever we have the result of an interpolation between multiple objects, we can see the rest of all objects. We don't have a defined or new 2D shape. Whereas with the Wasserstein barycenter, each time we do the interpolation, we have a new object with new geometrical properties. So the optimal transport is, or the Wasserstein distance in the optimal transport theory is a strong tool for comparing geometries and conserving the geometry after applying, for example, here 3D or 2D interpolations. Okay. So here we have another example. So we have a painting above, which contains the colors that interest us, and just below we have an image with the fruits, which we would like to recolor with the colors, of course, of the painting. And by doing the transport in the color domain, we have a new image with the geometry, with the initial geometry of the image below, but with new colors, which are the colors of the painting. Oh, yeah, okay. And now I'm going to speak about the origins of optimal transport. So it started with the French mathematician Gaspard Monge, 8 years before the French Revolution. And this mathematician published a memoir where he asked the question of how to transport a pile of sand or dirt from one place to another with a minimal cost. If we want to explain this with notations, we have in the image on the right two distributions. We have the red one, which is the source distribution, and we have the blue one, which is the target distribution. So we want to move from one distribution to another with minimal cost, and the cost here is C of x and y. So the goal is to find the mapping between these two distributions, which tells us where each point should go in order to have the final distribution muti and with a minimal cost. So this is the goal of optimal transport. So the goal is to move from one initial distribution to a final one while minimizing the overall cost. Here we have a simple example that illustrates the idea behind optimal transport. So we have 4 bakeries distributed in this way, and we have cafes that are distributed in another way. And the goal is to take the croissant from the bakeries to the cafes while they are hot with a minimal effort, of course. So we have 24 different ways from moving from bakeries to cafes, and the goal is to find the optimal configuration that makes us take the croissant from the bakeries to the cafes with an overall minimal cost. So if we consider the cost as the distance between each bakery and each cafe, the goal is to find a configuration that minimizes the sum, the total sum of the distance. So here we have 2 examples. On the right, we have a non-optimal configuration because the overall cost is 25.7, whereas on the right, on the left, we have a possible optimal configuration because it has a minimal lower cost than the first one. So this example illustrates that optimal transport is going from one initial configuration, one initial distribution to a target one, a final one, with while minimizing the total cost. Okay, so now we're gonna move to the definition of the Wasserstein distance and introduce some notations. Here we have two distributions. We have the source one, mu s, and the target one, mu t, and the costs of moving from one point from the source to the target is in the matrix big C. And the goal is to find an optimal mapping that tells us how to move from one distribution to another while minimizing the overall cost. So the Wasserstein distance is the minimum of the scalar product between phi and c. So phi is the optimal, is the transport plan, and here the minimization is done over this transport plan. So the distributions mu and s are here in this example are Dirac distributions, so there are some of Dirac masses. For example, for mu s, the masses are ai located at locations xi, and mu t is a distribution which is a sum of Dirac masses as well, and the masses are bj located at locations yj's. And so C is the cost, and pi is the set of all coupling that have mu s and mu t as marginals. So when we do the transport, we have two constraints to satisfy. The final or the optimal transport plan should satisfy two crucial conditions, which is the sum over the lines should give us the first distribution, and the sum over the columns should give us the second distribution. So these two conditions are very necessary to satisfy. Okay. So now I'm going to speak about the regularized Wasserstein distance. So it's the same definition, except that here we extract the entropic energy multiplied by an entropic coefficient, which is gamma. So why do we do the entropic regularization of the Wasserstein distance? Because it has many computational advantage, actually. Well, first, it makes the problem strictly convex. It means that the minimum is unique, which is really very convenient in optimization problems. Whenever we know that the minimum is unique, it's a good thing. And the advantage of the regularized Wasserstein distance is using the Sinkhorn algorithm that speeds up the computation. Okay, so now we have the formulation of the fusion problem. So now we're going to go back to our fusion problem. So the minimization, so the fusion problem is modeled as the minimization of the sum of two regularized Wasserstein distances. So the first Wasserstein distance is between u and I of f. So I is a spectral inversion operator that brings the multispectral image f on the same grid as the high resolution image u. And The second regularized Wasserstein distance is between U and J of G, and J is a spatial inversion operator that brings the hyperspectral image on the same grid as the high resolution or the target image. So gamma I and gamma J are the regularization coefficients, and these Wasserstein distances. So we can see the first Wasserstein distance between U and I of F as the one that carries out the transport of the spatial resolution from the multispectral image into the target image. And the second Wasserstein distance, we can see it as the one that does the transport in the spectral domain, which brings the spectral information into the target image. And you can notice that these two images are weighted by they have two weights, gamma, lambda, and 1 minus lambda. So these weights, they give us the possibility to choose if we want to have more spectral information or more spatial information. So gamma is a trade-off parameter. Okay. Here we have the fusion scheme. So we start from two noisy images, a hyperspectral one G and a multispectral one F. We do the denoising in order to reduce the noise from the images, because we recover them noisy most of the time from the sensors, from the satellite sensors, and then we do the spatial or the spectral deconvolution in order to bring these low resolution image on the same grid as the target or the high resolution image, and finally we do the Wasserstein barycenter. So here we have visual results. So we have the ground truth and we have a hyperspectral and multispectral image. So we generate these two images and then we compute the barycenter with our method that I presented in the previous slides, and then we compare them. We compare the results to state-of-the-art methods. We can see that visually the result is really pleasant. It looks like the ground truth, and yeah, we can see that the fusion works really well. And in order to spot where the fusion failed and where the fusion succeeded, we did the RMSE and SAM mapping. So RMSE is the root mean square error, and SAM is the spectral angle mapper. It measures the spectral quality of the fusion. So here we have, the more we go towards the red color, the bad the fusion. For our method, we can see that we stayed in the blue for there's no point that goes to the red. We have some points that are in light red color, but most of the time there are no big errors in the fusion. And for the state-of-the-art methods, we can see in some of them, especially in the CNMF, that there are some red spots, and we can see some light colors in the images, which shows that there are some mistakes, or in some spots the fusion didn't go correctly. And in order to compare objectively, we compared our method. So here it's HMWB, hyperspectral and multispectral Wasserstein barycenter, and we measured the performance of our method with many quantitative measures, RMSE, PSNR, airgas, SAM, Q2N, CC, and DD. So the PSNR is the peak signal to noise ratio. The airgas measures the overall quality of the fusion. SAM is the spectral angle mapper. Q2N measures the quality of fusion as well. CC is the cross correlation, which measures the spatial quality of the fusion. And DD is the degree of distortion, measures the distortion in the spectral domain of the fused image. So we can see that for all these measures, our method performed really well. And yeah, in all the measures, it overcame the state-of-the-art methods. So these experiments were carried out on the Pavia dataset that was taken over the Pavia University in Italy. The size of the image is 256 by 256, and it has 93 spectral bands. The images were corrupted with Gaussian noise, and here the RMSE and DD values are provided in a magnitude of 10 to the power -8. So that's it from my side, and if you have any questions, please don't hesitate.
So if you have any questions, please feel free to write them in the chat, and we will then display them to Jamila so that she may answer you. Appeared, so you can start the Q&A session, Jamila.
Okay. VAD applications are used. I don't understand VAD. What is VAD? What applications are used for? Still, the question is quite vague for me. Applications in what? I mean, of the fusion, of optimal transport? Sorry, but I still don't understand the question. I don't know if you got an explanation from the person who asked the question.
I will send this question and.
Okay. Have you developed software to do the fusion? This is indeed very technical. Yes, I can agree. It's very technical. Well, I didn't develop any software, but I did the code. I coded the Wasserstein barycenter and the HSMS fusion. But at this point, I don't have any software. It could be something that I should do in the future. It's a good idea. Yes, sure. I have a paper. Link. Yes, I can give you the link. So maybe I can send it to Benjamin later, and the Benjamin will forward it to you. Well, if you just type my name and surname, so I have a website, and you go to my papers, and there's you will find the name of my paper, but I can.
Sorry, I had a.
Okay, super. But now I have the link. Where should I put it, Benjamin?
You can put on the chat if you want.
Okay.
and we will.
Do you have it?
Yes.
Perfect.
Thank you, Jamila.
You're welcome. So, thank you for the presentation, Jamila. Thank you, Diogo. Regarding image fusion, at first it seems very distant from the common user. Do you think it can be used more often for common applications? Yes, actually. So we can. So I call it hyperspectral multispectral fusion, but if I say super resolution, maybe it's gonna be clearer and it's gonna ring a bell. So actually, it is super resolution. We can see it as increasing the spatial resolution of the hyperspectral image. And yes, this could be used in many applications because sometimes we need the hyperspectral fusion and the hyperspectral resolution and the spatial resolution to be on the same image for multiple purposes, for object detection and for analyzing the spectral response of the object. So having both information on the same image, it can be really helpful following some applications. So yes, definitely. I hope I answered your question. Great presentation. Can you recommend some resources, some resource books to learn more about the data fusion, in particular satellite images? Yeah, sure. I mean, there's so there are many people in France. So it's a French thing. Gabriel Perret, he did really a lot of stuff on this. I'm gonna write his name, and he has a book that you can access it for free and which is really well written. So Gabriel Perret, there you go. Just check, write his name, and you're gonna have access to the code. He has a GitHub repository with codes, and everything is explained well. I really like it. So I advise you to go there. I need to refresh some math, I guess. Do you have details on the benefits of your method with the other one in terms of performance? Of the benefits of my method, so each method is different. I mean, I just suggested a different method which is based on optimal transport for super resolution, and it's the first one as far as I know. But maybe one of the benefits of my method is it's fast because I use the Synchron algorithm, and also when I showed you the performance with the comparison of the performance with the other methods, there were some spots where my method performed better than these methods. So, I mean, from the results, using optimal transporting the mass contained in pixels from images conserves the transports efficiently the resolution into the target image and makes the fusion better. Yeah, this is what I can think of. I will admit I was a little lost in the math. Could you maybe briefly explain what the formula does in mathematical terms? Yeah. Okay. So which formula? Because there were. Okay. So let me find the formula. If you want to, if you're talking about the Wasserstein distance. So the Wasserstein distance is just you minimize over a variable, which is phi here, and you minimize the scalar product. I guess you don't need a very high level in math to know the scalar product. So scalar products between two vectors, it's just you multiply elements by elements, and then in the end you do the sum. So this is really it. And the goal is to minimize this scalar product between the cost matrix, which we computed before starting the computation, and the unknown transport plan. So the Wasserstein distance is really this, and the regularized one. Actually, we regularize it because, as I said, it has many computational properties. Sorry. We extract the entropic energy to make the energy strictly convex, to have a unique minimum. So because it's difficult actually to compute a transport plan, or sometimes it can be really difficult because first, for memory issues, the transport plan can it can be really huge. In the images I showed you, it can we have more than 1 million pixels, very, very easily, and no memory, no RAM can contain such an amount of data for computation. So we find some computational tricks to approximate the Wasserstein distance. Actually, the regularized Wasserstein distance is an approximation to the Wasserstein distance, but at the same time, we want to make the computations easier and faster. Can you handle cloud cover in the Fusion? This is a good question. I've never considered cloud. To be honest, the images I used for the Fusion didn't have any clouds on them. So yeah, so this is something to dig deeper. I don't know, to be honest. Can we implement that Fusion code in Python environment? It would quite help them all. Yes, absolutely. Actually, I already wrote a code, so thank you for your question, and I will make it public very soon. Yeah, so I already have the code in Python and in PyTorch too, so that we can use the GPUs. So yes, I will make it public very soon so that people can use it. Can you explain how you ended up studying this method process, please? Okay, this is a funny question. Well, so it was my PhD. My supervisor worked with optimal transport, and when I arrived in my PhD, we talked about it. It was quite new, very interesting, and yeah, we just started working with it because no one has ever considered doing the fusion or the super resolution with optimal transport yet, and we knew that it had good results. For example, the 3D interpolation that I showed you, yeah, it gives really pleasant and good results, and we were like, let's try it for the fusion and see if it works, and it works. This is how I ended up doing fusion with optimal transport. Where do you get the hyperspectral data from? This is a good question. In our domain, there's a big and huge lack of data. So the Pavia dataset is very easily accessible. So Pavia Chikusei, which is provided by the researcher Naoto Yokoya. I'm going to write his name. You can access it for free. And you can also get data from fusion contests, organized by IGARs. These are the main sources of data, but I can agree with you that there is not much data out there, especially the hyperspectral one. And if you just type hyperspectral data for free, you will find a few things on internet, but there are not many things actually out there, which can be a limitation if we want to do hyperspectral multispectral fusion with machine learning based methods, for example. Okay.
For your Q&A session. So if anybody have another question, please feel free to ask now. There is one coming.
There's a new satellite from ASI that provides hyperspectral data. Do you use it? No, I didn't use it. No. I know that there are also satellites missions by the Italian space agency, Prisma, I think, and they started providing data, hyperspectral and panchromatic data, not very long ago, so that can be really useful. So a panchromatic image is an image with a good spatial resolution, but with only one band, not like the multispectral image that has many bands. Let me just I'm just gonna send you something. I'm not okay, I've never, yeah, okay, I think it's this. So this is the web page of the Prisma. So maybe this is what the person who asked the question meant. Yeah, so I think we're speaking about the same thing. So I'm gonna send you this link. So the data was released very recently, and I haven't got the occasion to use it yet, but it would be really a good idea.
Okay, so we do not have any more questions. So I think we can close your part of the presentation now and go to Øystein. So thank you very much, Jamila, for both your very interesting presentation and for the Q&A session.
Thank you.
So thank you again and see you later.
Thank you. See you later. Bye-bye.
Goodbye. So welcome, Øystein. I will now start your presentation, and the floor is now yours.
Great. Hello, everybody, and you're very welcome. Greetings from Ireland. Oisin McGrath is my name. I'm the CEO of DroneSAR. So just to give you a little bit of background on my own career so far, it's been heavily aviation-based. I did a degree in aeronautical engineering. I went on there to qualify as a pilot, fixed-wing pilot, first of all, early in my career, followed by airline transport license in helicopters. I now serve as the chief helicopter instructor in the Irish Air Corps. My role then went from helicopters into the RPAST or UAV industry, and I am now the chief UAV instructor for the Irish Air Corps and the Irish Defence Forces. And I also have two businesses outside of the military, one of which is a drone training company, and we train international students in drone training and education. And the second is DroneSAR, which is a software-based company, which is drone-based. So, good background in aviation, all coupled into develop this company, which is DroneSAR. DroneSAR was founded in northwest of Donegal, a little town called Letterkenny, where at the time DJI, the biggest drone manufacturers in the world, were partnering with ENA, the European Emergency Numbers Association, to put together a study on drone education and how drones could be used in emergency response. And from the report, there was a lot of recommendations that were made. For example, the drones didn't really fit into emergency response without communications. They had no way of automatic flight patterns. There was no way of sharing information. And we designed a software based on the information that was provided in that initial study, and followed on with a second phase 2 study. So DJI gave Donegal Mountain Rescue Team a number of drones for free, strangely enough, for us to test this software in the rescue environment in real-time scenarios. So that's kind of the foundation of DroneSAR, where it comes from. And throughout our time in the last 3 years, we've had a number of startup awards, been backed by Enterprise Ireland, Copernicus Masters winner in the Services Challenge satellite navigation winners regionally in Ireland. We've been involved in the ESA-BIC Business Incubation Centre and Horizon 2020 projects based on our integration of satellite technology with drone technology. We partnered with DJI and also a number of companies throughout Europe, also involved in the emergency response sector. How does it work? So at its most basic level, DroneSAR provides a link from the pilot to the drone. So in the field, as they fly, it feeds back video from the drone to an iPad, and the pilot can control the drone using a number of automatic in-flight functions. And the functions are actually based on the flight management system of a helicopter. So automatic flight patterns, sharing locations, drop pins, dropping positions, marking on target, all of which we'd have in our own helicopters, rescue helicopters here in Ireland. So it's very much based on that concept. However, we found that even though the pilot was in the field, he's not necessarily the subject matter expert. So the information that was sent by the drone had to be sent elsewhere to the subject matter expert, as he might not be there. So the next level up for the DroneSAR software was that it provides the autonomous flight, which can be shared, which can be passed from a web-based program to the pilot. So the subject matter expert can sit in an office and manage a load of drones that may be operating in different areas, and he can send missions to each of the pilots. As the pilots find information, they share location back to the command and control center, and then only relevant information is displayed, as there could be a lot of information displayed. And the pilots have a number of in-flight functions. They have pilot chat, they've got a two-way audio channel, all of which they can connect directly to the command and control center. So that's the basic level of DroneSAR in terms of the connectivity. It's the first level of connectivity. So using kind of satellite technology, we kind of brought in the Copernicus imagery, which I'll talk about in a second. But the idea here is that the DroneSAR system connects everybody, and it connects the pilot who's in the ground to the team member, to the browser logged in from wherever anybody wants to log in from. Whoever has the login details can watch the drone footage live, see what's going on, and appraise any images. And essentially what we're doing here is allowing anyone to have an input into a search pattern which is live. So we have more eyes on the footage basically to help find the missing people or wherever that might be. The live browser then on the command side would look something like this, where on the left side you have the image of the drone flying its path across the ground in a 3D imagery. So the command and control have a clear image of the terrain, the features, how they're going to resource it. If they need to send extra resources, how are they going to do that? Can the helicopter be used? Can they put people on the ground? On the right side, on the bottom right side, you can see a 2D image of the exact same mission, which is just a 2D image of it with the drone track. And this is what the command and control would see. And then on top then is the archive function. So following missions, all missions are saved, archived, and command and control can go back and watch these missions retrospectively after the missions have taken place. So in the event that somebody isn't found, they can see afterwards and go and review the footage a second time. As well as having command and control and the pilots connected, we also designed a DroneSAR Team app, which is an iOS and Android team app. And once you have a login, it allows anybody from a mobile device to log into that same system. It allows you to screen grab imagery, to draw on it and appraise the image, and to send it to command and control for feedback also. So again, it just serves as another way of connecting people during a search. And this can be done from the comfort of your living room. If you're not involved in the search itself on the ground, that you can do this from a control room. So everybody's involved all the time. So on to the next slide. So the Copernicus link, following our win at the Copernicus Masters, we were in touch with a lot of companies and projects where we had come up with an idea of how to use drones in emergency response, and in particularly hurricanes and severe disasters, flooding, for example. So all drones use a Google mapping service or Apple Maps or a different map server, which could be 2 or 3 years out of date in terms of satellite imagery. And that's not very useful for command and control, nor is it useful for a pilot. The pilot needs to be able to see the area that he's going to search in real time. And we came up with the idea of having up-to-date Copernicus imagery from the emergency services satellites to overlay as images on the pilot screen and also the command screen, so they have a better view of what's actually happening on the ground. during or post disaster. For example, on the left side, you here see a basic image of what would be seen on the pilot side pre-disaster, but following a disaster, you'd see it's the exact same area just post-disaster. So you have a more up-to-date image of what's actually going on. It would give a better idea for a pilot and where he wants to search and where is the most effective area to search rather than guessing. So it basically helps with better informed decisions. So using this concept, we on our own DroneSAR browser, as well as having overlaid satellite images, we can have a number of drones operating with a slide scale. My phone would ring. On a slider scale, where we would have the old imagery and the new imagery on a slide scale, and allow the drone pilots to have their drones displayed, and all the command and control can see where the drone images. And you see the bottom right hand image would be the images taken by the pilots. The images are all sent to the browser, and the images can be appraised through the command and control system of the affected area. So in effect, what we have done is allowed drones to become part of a layered network of satellite imagery. The Copernicus layers and the various Copernicus satellites provide a number of different levels of data, but can be restricted due to cloud cover, for example, poor weather, and obviously the use of satellites sometimes can be complicated. Drones are cheap, they're effective, they're low level, and we have allowed the drone system to feed from the bottom up, I guess, while the satellites feed from the top down. And in a way, would look something to what you see on the screen, where you have a DroneSAR data, a drone providing imagery to a browser that can be overlaid with a number of Copernicus layers from satellite imagery. So of late, we've been involved, we were invited to be involved in a project which is an ESA, a European Space Agency funded project called BSURE, which stands for Brilliant, I can't remember. Survival in Urban Resilience Excellence. My mind is going crazy here. The phone is putting me off. So the BSURE project is a collaboration between a number of European countries. We have Ansor Technologies, who have a very clever ground-based application for smartphones to allow people to report in real time during disasters. iGeotech is an Irish-based company, kind of artificial intelligence and browser development. Johanniter is German. Anchor is another security company in Norway. And we've been dealing with the AHA Center, which is the kind of Asian disaster management agency, UNDAC, UNISAT, United Nations. And with input from all these people, we have come up with a browser system that allows the general population to provide feedback and information in disasters as it happens. So using their smartphones, taking images, sending them to a central server, flying their drones, using DroneSAR, providing imagery and video to a central server, all of which then is used to allow command and control to make better informed decisions on disaster management and risk assessment. Yeah, so that's kind of where we're at. Very, very quickly, we, I suppose, came from a very simple report back 3 or 4 years ago, and now have been heavily involved through a number of Irish agencies, the European Space Agency, and involved in multi-million euro projects and partnerships throughout the world. And from here, our next goal is to incorporate this into hopefully disaster management response agencies throughout the world, and also to bring in the artificial intelligence suite into our DroneSAR program to allow a more accurate people detection rather than relying on people appraising images. We can try and let the computers do that, but that depends on us collecting data, and the data that we collect will be used to advance our software into something more applicable to the modern world, I guess. So that is it from me. I guess I can open the floor to any questions from here. Thank you.
And once the first question come in, we will display for you to answer. Hello everyone. Sorry, we have a small problem with Oisin's connection. So once he come back, we will start the Q&A session again.
Hello.
Welcome back, Oisin.
Hi. I'm not sure what happened. Apologies. I hope I made it through the presentation without any interruption. I'm not sure.
Yes,
I hope I did.
no issue on your presentation. Just this one where you froze and got kicked out from your connection.
Okay.
So you can go back to the Q&A session. No problem.
Okay, great. Thanks. Okay, DroneSAR in relation to simulate and prediction of critical infrastructure. We don't have that facility to use artificial intelligence to I suppose predict any sort of critical infrastructure destruction. What we do have would be a provide automatic flight over the affected area and to share location. So we don't have to, we through the B-Shore project, the artificial intelligence has been designed for once the images are sent back from the drone to the B-Shore portal with video and with images, then that can be simulated through the B-Shore portal, but not on the DroneSAR software itself. How much money do you have, Aston? Yes. Yeah, well, flying anything in a volcanic eruption has a number of issues with volcanic ash. Obviously, aircraft engines, helicopters don't fly very well in volcanic eruptions. Drones are electrical. So, yeah, I would say you can fly them. It would be quite tricky, and you'd have to be prepared to lose the drone. The beauty of a software like DroneSAR is that you're providing imagery back to a central server. So if you did lose the drone, for example, you still have some sort of archive function back in the command and control center rather than being stuck on the SD card in the drone itself. So I suppose in short, yes, but be prepared to lose your drone if you need to, if that was the case. Yeah. The reception has been good. The funny thing about disaster management agencies is that they won't buy things unless it's been tried and tested. So that's kind of where we are at the moment, is trial and test. Well, it's products, but we are in I suppose, a test phase in terms of agencies and use cases. Our Irish Coast Guard here in Ireland and our civil defence use DroneSAR all the time. So we have got very good feedback from them. So we're constantly using that case to try and introduce it to other agencies. The scope of training is minimal because the software is designed similar to the DJI software to allow people to operate it themselves, and actually with minimal input. There isn't really much case to have a software that's very complicated for people and it's overcomplicated. So we use, we've online videos. We also have instruction manuals and quick start guides to allow people to pick it up very quickly. And in fact, it's quite simple. And in fact, once you can log in and you've got good connections, it's quite easy to figure out. Expenses wise, the software is only €360 for the year, or there's a monthly cost as well. I think it's €35 per month. So it's actually quite low. Again, we're very aware that public agencies, volunteer agencies, their budgets are quite low. So we had initially price point a good bit higher than that, but since we before we released, we came back on that on the basis of that volunteerism, I guess, through agencies. What does the training of drone usage look like? Are the rules of engagement and targets or points of interest? Yeah, well, drone training, first of all, the European Aviation Safety Agency, or EASA, have just released a new set of regulations which come into effect at the end of this year, and they have recommended a number of rules that will be implemented to each national authority, and from there, national authorities then will decide on the level of training that is required for each category. So even though EASA are looking for what would be called a single European sky effect, where if I get qualified in Portugal or Spain, that I can fly in Ireland and France and all these different places on the same training. So that's kind of where we're at as a company outside. We are pushing to have our course, I suppose, regulated by all the authorities, which one qualification would do you for a number of countries. So that's actually quite simple. It's a fully online course with a full online examination, so actually it can be done fully remotely, and that's what we've set up. In terms of rules of engagement in the military, yes, obviously rules of engagement for targets in terms of release of any ballistics. If you're speaking about rules of engagement in terms of taking photographs, there are data protection issues. If you were to do it to your neighbor, for example, that would not be allowed data protection. However, in an emergency scenario, I think when somebody's life has to be saved, I think all bets are off in terms of what you can and can't do. And it's the same with search and rescue and helicopters. Once it's a rescue scenario, the rules don't really apply, and the saving someone's life becomes the forerunner. So the rules would tend to be less when you're in a search and rescue scenario, and disaster management will fall into that. Yeah, well, actually, that's a good question there, Jason. Yeah, the Naval Service haven't used our software. They do use drones. We train them, and they have had a really positive effect in the Mediterranean operations. They were using drones to great effect. And drones are usable in the maritime sphere. The problem with commercially available off-the-shelf drones is that they have limited battery life and limited flight time. However, something a bit more long range would be more effective in the maritime sphere. I suppose using drones off ships, especially commercial drones, while they can be effective at short range, the length of flight is an issue, and the weather is an issue, and battery life is always going to be an issue, and connectivity is an issue. So you'll get video footage back to your operator on the ship, but however, trying to transmit that in the absence of mobile phone networks or 3 or 4G networks, for example, it has to be done by satellite link, SATCOM, which is very expensive. So there's a little piece there that's easy enough design, but it's an expense thing. So yeah, it can be used limited. But if you want to use a drone that's effective in the maritime sphere, you're going to have to spend a bit more money. You could be looking at six figures there, high end 6 figures, or maybe 7 figures. Yeah. How have I addressed the battery life limitation? The battery life limitation is actually a limitation worldwide. Unfortunately, that's just something that exists. That's a technology thing. There's been a number of attempts to go from the LiPo lithium polymer batteries, of which the drones are, which now, I suppose when drones came out, they were 15-20 minutes. Now it's 35-40 minutes on the commercially available drones at €100 per battery. It's not bad. There are studies being done to increase battery life using on a number of different methods, to using various different chemicals to increase battery life. Again, with that comes expense. Research is expensive, needs to be funded. It's going to be a long time before anything actually works. If you really want something to fly a long time with long range, you're going to be looking at aircraft fuel, aircraft engines, maybe petrol engines, model aircraft engines. That'll be the next step up, and then obviously pushing into normal aircraft propeller and jet engines from there. So you're adding expense every time, but at a lower level, I guess it's limited by technology, worldwide problem. Yeah, I just covered that, Martin. The DroneSAR will work operating directly to the pilot, and it'll feed back to the pilot at its basic level. Automated flight patterns, waypoint missions, and feeding the footage back to the pilot will work because it's linked to the drone itself. Where you'll run into trouble here will be that the link to the command and control unit is using a 3 or 4G network, unless you have access to a SATCOM. Again, that's expensive. That's a limiting factor at sea because you're outside mobile coverage. The ability to detect the person in the water is down to the pilot. Obviously, field of view of the camera is an issue, and search area will be small. However, the way we've kind of based our business model will be kind of we'd be kind of coastal and land, really. Anything from seaborne, I guess, and out into the maritime area would have to be something a little bit more robust than a DJI drone. I think, unless you're only talking about a couple of 100 meters offshore. Yeah, with drones, we've trained a lot of the fire brigades here in Ireland as well, and we don't use the artificial intelligence at the moment to monitor forest fires. Drones have been used. There aren't really issues at all with the drone connecting between the drone and the operator. That's never an issue. That's just a Wi-Fi signal between the drone and the operator. Nowadays, drones can go 5, 6, 8 kilometers without any interruption of video signal or drone signal. And usually there's 2 antennas over here. One is for control and one is for video. So they're generally pretty strong, and you can buy little amplifiers for them. So that's not a problem. The problem that you will end up, that you could run into with any software, and this is again, this is a global problem. This isn't just DroneSAR. It's at times in disaster areas, mobile networks can be down, and then transferring that image, that sort of information, be it by mobile phone or any sort of transfer of data, is impossible until the networks are back up again, unless, again, we have access to satellite communications. Personally, no. I'm joking. Do we have a problem with birds? Yeah, it depends country to country. We have had issues of larger birds of prey dive bombing on drones and stuff. Yeah, again, depends on the area. It depends on how close you're flying to them. If they see it as a threat, they'll obviously attack. If it's not flying in a threatening manner and out of their area, then they won't. It's a big area you can take at a single flight. What is the distance per pixel? That is a good question. I'm not sure of the distance per pixel. I'm certainly not sure of that. The algorithms based in DroneSAR are based on the field of view of the camera versus altitude versus air versus drone speed in meters per second. And the images are taken based on that. So the pilot chooses altitude. There's a certain amount of overlap as well on each leg. So in a search, every area is covered. The height at which the pilot wants to fly, again, is going to come down to experience as to what they can see at various altitudes. And I think that's just a personal choice. As a person who has experience flying and experience with aerial search and experience seeing the different, I suppose, contours and shapes, then I would probably tend to fly a little bit higher because you tend to pick up things a little bit quicker. At a lower level, less experienced guys in the Coast Guard when they were starting tend to fly a little lower because they were slower to pick things up. So I think that's just down to personal experience. Aerial search is a complicated area, and it's certainly in this day and age when ground teams have suddenly become airborne, that is very loose, and it's one that people should definitely watch out for. In terms of georeference, yes, all the images that are taken are geotagged with the lat long information, all the geo information that's in there, metadata. So yeah, that can be used afterwards to drop as a TIFF file onto maps. Yeah. Our way forward being disaster management in Africa. We had a contact in South Africa before. There wasn't much really moving down there, to be honest, and we haven't really done much down there, to be honest. No reason why we can't do that down there. It would work perfectly fine. At the moment, our focus is on the projects, continuing with a customer support, and in terms of big launch, we're going to wait until we have a properly refined disaster management software to kind of give it a big launch. But certainly, if there was agencies who were
it seems we have a problem with Oisin's connection again, so I will. Okay.
If there was scope for agencies, you can go onto our website, send me a note on the chat or by email. We can certainly have a conversation about that. Yeah. Maritime search and rescue in open seas with drones from a mothership may take advantage of the images from Sentinel-1, 2, 3, and other. I don't see them one being used over the other. I think the important thing to remember here with drones is this is something that comes up quite a lot. Drones are another tool in your toolbox. They're like a mountain rescue team's waterproof jacket and pair of waterproof boots. They're like a maritime-based rescue agency's boat and their maritime rescue gear and immersion suits, and like helicopter pilots' helmets. And it's another tool, it's another thing that teams can use to make their jobs either easier, reduce risk, increase safety, and increase effectiveness. In terms of taking one over the other, certainly don't see there one being better, where there's going to be pros and cons to both. Obviously, your Sentinel images, you've got various different filters, you've got various sizes, it's fast. It takes time, however, to get these satellite repositioned over areas. It costs a lot of money. On the plus side for drones, it's very cheap, it's very easy, it's very effective, little training. However, there's limitations with weather, connectivity, all those nice things. But however, they're very complementary. I think massive cloud covers, covered in areas, well then the drones can provide nice, very clear imagery underneath the cloud images, which actually can be stitched together into a nice single image. So I think while they may not be one better than the other, they certainly complement each other, certainly at a basic level. Do we use the Matrice DJI series? Yes, yeah. We use the Matrice series. We've used 210s, 300s, and we use all of the DJI machines, Mavic, Mavic 2 Air, Sparks, Phantom 3s, 4s, you name it. We've used them all, Enterprise 2, thermals. Is any other company besides DJI? We don't use any other company. Our software is based through DJI. We partnered with them to design a software for DJI drones. They're clever. But I have had experience of some of the other drone types, and I wasn't a massive fan personally. So our, I suppose, group have kind of gone one direction with it. Unfortunately, that's our kind of business model. How can we engage DroneSAR tech in other EU countries outside of Ireland? Yeah, look, the DroneSAR website is there. It's just dronesarpilot.com, and go on there. It has a bunch of stuff, manuals. Send me an email. I think it might come up here at the end. You can certainly get it from the website, or send me a message on chat. It's certainly easy to download. Go on the App Store with an iPad as a free 30-day free trial. So you can have at it, guys. Go for it. Download it, try it, see if you like it, and get in touch if you do. How the 3D images were available so quickly. The 3D images on our browser is actually the 3D image from the map, which is, it's nothing to do with us. We're overlaying our drone track onto the 3D image, which is already there. So that that's a Google Earth algorithm. The 3D images on the drone is another software. We don't do that. We concentrate on immediate imagery, photographs, high definition photographs and video for people recognition. There are companies like Drone Deploy, for example, will allow you to fly the drone, take images, send it to a server and come back with a 3D image, and you can examine each corner of the 3D image. That's certainly a way. It takes time. Again, our method was immediate, in the moment response. We didn't want to wait for 6, 7, 10 hours for a server to come back with images, when potentially you could be looking at somebody that was alive in the image and then could since have passed away, or method of I suppose software, using the software was immediate response. You have to talk to me offline, Jason. It could, yeah, is the answer. That's funny. Yeah, it could. It certainly could. It's the same. It's the same as the AIS, marine AIS. It works the same way. So it's, yeah, certainly can do. Yeah, that's a good question though. How far away from an all-weather drone? It is not far away. We have commercially available drones, probably not so much. They are IP rated now, so there is a certain amount of waterproof to them, but I wouldn't rely on it. If you want to have a full weather, all-weather drone, you're going to want to spend a lot more money. Again, it's never going to be perfect. As I said earlier, a drone is just another tool. And it certainly isn't going to solve all your problems and flying days that helicopters can't. I think that day is a bit far away, but it's not far away. I think technology is changing at a rapid rate, so it certainly isn't far away. Yeah, and that's something that has come up. That's a good question as well. For 3D, have two cameras mounted with kind of intersecting images. That will certainly give a certain element of kind of a stereo image or a 3D type image. The problem with that is having two cameras on a drone, on a gimbal. One, it needs to be a fairly heavy lift drone, because they probably have to be heavy, high definition, expensive cameras. And two, you need gimbals that operate, one gimbal that operates together to get the correct angles for the various altitudes for the proper amount of overlap. So it's a pretty complex area. It certainly is possible. But again, you're looking at money. I think the big thing for us here is with DroneSAR is we're aiming at a lower level of cost here. You know, a DJI Mavic Enterprise 2, which is a higher end drone, costs €2,000. That's where we're at. If you're looking at 3D cameras, two cameras with a big drone, you could be looking in the region of 50, 60 grand easily before you even add cameras and software to put it all together. So you could be looking at 100 grand. Yeah, drones have been used already with special sensors for air pollution measurements. One of the projects we were involved in was this is a separate project. It was like an urban resilience project. They were able to use drones, one for air pollution, for gas particles, any sort of air particles, which was fed back immediately. And then the other was that they were able to detect heartbeats subterranean. So as the drone flew over the rubble, they would be able to detect signs of life underneath the rubble. So there's just so many applications for drones. Once the software is there, I think the technology can be added to them to make them into whatever you need, I guess. Yeah, we use thermal cameras all the time, and unfortunately, well, I suppose fortunately, DJI have, with the Mavic 2 Enterprise at €2,000 or €2,500, that has a thermal camera. It's got a dual daylight and thermal camera. When we started DroneSAR back 3 years ago, it was €5,000 for an infrared thermal camera on its own without the drone, and then you'd have to buy an expensive drone to put it on. So the day of having thermal cameras now is pretty out there. It's available off the shelf. You can buy it online, and those drones are extremely effective in terms of thermal imagery. No, I don't think two drones. Sorry, it was two drones flying in tandem with camera overlap. I don't know if that could be done. I guess it could. I suppose the thing is, why would you want two flying is to get instant 3D images. I think that would be really hard to pull together. It's probably possible, yeah, it's a good question, but I don't know if the software is there to drive it. It certainly doesn't exist now. You might be onto something there. Yeah. What was our last mission? For us, we have done missions. It was many years ago when we were doing our test phases, but we generally don't get involved in the missions. What we do is liaise heavily with the Irish Coast Guard for their missions. So they do the missions, they give us operational feedback on how what worked and what didn't work, and we amend the software accordingly. So we don't actually fly missions outside through DroneSAR. Through the day job, it's another thing, but the Irish Coast Guard are on regular operational missions using drones, be it for searches, area searches, risk reduction missions. They're doing it all the time, and they find the drones very handy for that kind of stuff.
But we still have a few minutes, so if anybody have any more question, now is the moment. But since you already answered a lot of questions, I think we may have an all-around horizon of participants' questions.
No problem.
So I think we can conclude the event here if there is nothing more. So thank you very much, Oisin, for your presentation, for your Q&A, and